Sprinkles or Mirrors? You can see the title. Discovering the True Nature of 6-metre Sporadic E. Chris was the recipient of this year's RSGB Les Barkley Memorial Award for his research into the sporadic E propagation at 50 meg. So for the first, I think you were the first winner, weren't you?
No, second.
Second.
The first one was that man there.
Ah, right, yes. Yeah, I remember. Yeah. Time flies, doesn't it? Yeah. So,
it does.
Perhaps surprisingly, sporadic E is once again becoming a hot topic in professional circles, and Chris has shown that it's possible to do some real science with amateur equipment, resulting in 2 academic papers so far. In this talk, he's going to explain the experimental approach, describe his latest results, and discuss some of his outstanding questions. If you don't know it, Chris was first licensed in 1971 as G8 Echo Uniform Bravo, upgrading to 4 FIX in 1979. In the early 90s, he got interested in Band 1 DX TV.
80s. Early 80s.
80s?
I might have written 90s.
Oh, right, sorry. No, it's late.
It's your eyes.
It's late. There's my eyes. Which led him to 6 metres and one of the earlier transmitting permits. Chris joined the UK 6-metre group and in mid-90s became the editor of its magazine, 6 News. After 11 years in that role, he switched to being the secretary of the group and is currently the chairman. Chris is also the secretary of the RSGB Propagation Studies Committee and since 2018 has been engaged in a part-time PhD at the University of Bath focused on sporadic E propagation. So, Chris, over to you.
Hello. Welcome to the graveyard shift. And thank you for not going straight to the bar. This is water, not gin. Okay, so thank you for that introduction. I wrote it, so it should be all right. So I just wanted to talk about my research. Happy to take questions at the end if I get through it quick enough. And to show you that actually doing stuff with science is not necessarily straightforward. You can't just say, oh, I heard so-and-so, therefore it was caused by a thunderstorm or something. But at the same time, you can actually do real science with amateur equipment. So I got into this particular question, this research area, which is all about the polarization, using the polarization of the signals that we receive as a measure, as a marker of what the hell's going on up there. And I became aware of some research by Graham G3TCT. This is GB3 LER as received at his station. And what he's done here is he's got a vertical antenna, this isn't it, this is mine, and he's feeding one, this is the Lysage's figures, if you remember that from your school days. And he's feeding one into the X and one into the Y, and that's what you see. Yeah, so that made me think, oh, that's interesting. And 2 thoughts came to mind. One is, oh, that's interesting. Can I find something else about it? By maybe taking a more systematic approach to investigating it. And of course, though, I'm a 6-metre DXer. I have been for 35 years. So can I use the information? Can I use the knowledge? Can I work out ways of working more DX? Those are my 2 questions. And so I replaced my existing 6-metre antennas with this thing, which is a 7-element LFA cross Yagi, 2 Yagis, 2 identical LFA Yagis on the same boom, and that has been my primary 6-metre antenna since 2016. So early on, I did some work just basically looking at the signal strength that I received on the 2 polarizations. I'm sort of in your way here, aren't I? Sorry. I'll stand back in. Well, you can always do that if you're actually interested in this. And this is just one example of what I saw. So the black line, this is like a pen recorder trace. This is a signal, an SSB signal from Sardinia received at my station. The black line is the signal strength on the horizontal antenna. This is using an Annan, that was actually a 100D dual receiver, dual identical receivers. So the black line is on the horizontal antenna, and the red line is on the vertical antenna. And you can see that whereas the horizontal and vertical are sort of about the same, maybe I ought to be pointing with this for the benefit of those who are viewing the video. Along this bit here, the two are roughly the same. But here, the horizontal signal took a real dive down to virtually nothing. And there's actually about 30 dB there between that and that. And I don't need to calibrate it because I know they're absolutely the same signal received on these two antennas. So that was sort of showing me something was going on. And I've presented here in 2016 on a whole range of measurements, and I showed that you can see these kind of variations on single hop, multi-hop, 2-hop, 3-hop signals on 6 meters. So polarization varies. It's not the only thing that varies, of course, because sporadic key signals are going up and down like the clappers anyway for other reasons. But part of the reason that your signals, certainly on this day, if I'd just been using my horizontal antenna, I'd have lost him there, is due to polarization fading and rotation, the orientation, which one is stronger, changes over time. Okay, so just a little bit about the ionosphere, because of course then on 6 meters F2 wasn't a thing in the sense that we were heading into solar minimum. So sporadic key is what I was focusing on. The thing about sporadic key is that it's different from the way that the rest of the ionosphere works. So you've seen diagrams like this, I'm quite sure, before. There's the F layer, or F2, F1, it splits during the day. And they're caused by ionization of gases in the ionosphere. When the sun goes down, the ionization mostly goes away. Sporadic key, though, is formed by a process of pushing together, concentrating thin layers of essentially metal ions, iron, magnesium, which are ablated, is the fancy word, burnt off meteors. And they know that's true because they've sent rockets through it. The line that looks like somebody's face here, the chin, that's the electron density. And sporadic key regularly is a lot more dense than even the F2 layer. F2 is coming back, hooray! But then, certainly, sporadic key was the only way we were going to work any DX on 6 meters. And it's not affected by the solar cycle. Now, when I got into this a bit more, and it was actually after my lecture here that I got in contact with the people at the University of Bath, some of them were here, and got into doing a PhD. They showed me the error of my ways in terms of the way that I was looking at measurement, because it's not enough just to measure the strength of those two horizontal and vertical signals. That doesn't tell you everything. It doesn't tell you if you've got, this one's twice the strength of that one. It could be that way, it could be that way, or it could be elliptical, and it can't tell you the difference between those things. So I needed to up my game, but fortunately they helped me with a new technique which allowed me to do that. So that then, as I started that work, I sort of realized actually there's a real science question here. It's not just about, I want to know what goes on because it's interesting, or how can I work more DX? It's actually about how does it actually work? And here's where the title comes from. Sprinkles is what the Americans call hundreds and thousands, right? So I actually started using this title with a presentation to an American conference. So is sporadic key specular reflection like a mirror, which a lot of people think of it as, and you'll find papers in the academic literature which refer to it like that. You'll find people who talk about scatter. Obviously, scatter does happen, but is that the main mechanism behind sporadic key, or is it just the same as the normal F2 propagation that we get on 28 megs or 21 megs, which is essentially a bending process. It's refraction, not reflection. But of course, the sporadic heat layer, as we know, as I've already said, is very, very thin, might be a couple of kilometers or less thick. So there's not a lot of bending room in there. So it has to be very, very fast bending. And if you're transmitting with a vertical or a horizontal antenna, if your signal is being scattered, it will either retain its original polarization, or the signal, depending on the size of the scattering centers, how the scattering is working, or it will become depolarized because all the scattering centers are out of phase with each other. If it's specular, it may well come back. Well, I mean, the idea of a mirror, a metal sheet in the sky, is obviously fairly fanciful anyway. But again, it won't change the, well, it will change the orientation of your linear polarization, but it won't change it into circular polarization. But magneto-ionic propagation, magnetic field, the Earth's magnetic field, in an ionized layer, which is what the ionosphere is. It's not very ionized, it's less than 1%, but nonetheless it is a plasma. So it's equivalent to what's inside those, well, are they fluorescent lights? I don't know. In there is a plasma, although that's been excited to make light come out. It's not a bit different. The magneto-ionic just means it's propagation in a plasma, which is ionized or partially in the presence of a magnetic field. And it's the Earth's magnetic field that we're talking about. So from the science question point of view, that's what officially my research is about, is answering that question. And the interesting thing is, nobody's done it before. And as it said in that blurb, sporadic key used to be a big research topic in the days of band 1 television because it caused interference to TV. They even used to use amateur reports in the 50s for mapping sporadic key. That went out of fashion as band 1 TV went out of fashion. But now it's coming back, and there are two reasons. Firstly, we have all those satellites, particularly, say, the GPS, GNSS satellites, and passing your L-band signal, your 1500 megahertz signal through a sporadic key layer, not surprisingly, causes quite a lot of disruption to the phase and the amplitude of the signal it's going through. Scintillation, they call it. And also, there's now a lot more interest, and there's even a climate change link to the way that the atmosphere, the weather bit, interacts with the ionosphere, the ionized bit, in this region called the mesosphere, lower thermosphere. And there's a lot of interest in that. So that's why sporadic key is now becoming more of a hot topic, but nobody's doing quite what I've been doing. So just as a bit of, you know, I'm sure most of you know this. So this is a linearly polarized wave. The red one is the electric field, which is the way we conventionally define the polarization, of course. It's the electrons zip up and down our antenna elements, and therefore this is horizontal. And on this diagram, the blue is the magnetic field, and you can see that the electric field is just, this is a vertically polarized wave. And of course, if you had a skipping rope, you can do that with it. If you're clever, you can do that with it, although you'd have to whip it quite hard, or even that. But you can also do that with a skipping rope. And you can also do that, or rather, radio waves also can do that. So this is a representation, quite nice, thank you, Wikipedia, of that's a right-hand circular polarized. In other words, in the direction it's going, your right hand indicates the direction it's moving. That's a linear one. Oh no, and now it's gone left hand. And the thing is that you can compose, well, any wave actually, into two components, X and Y on this diagram, but let's say horizontal and vertical. Circular polarization, those two are equal, and there's a phase difference between them of 90 degrees. Any other combination, in other words, if they're not the same and or the phase difference is not 90 degrees, then it's elliptical polarization. If the phase difference between them is either 0 or 180 degrees, it's linear. So arguably, linear is a special case of elliptical polarization. Now, hopefully, you'll be able to see this. And I will try and do this on the screen here. This is a representation of how a wave goes up to the ionosphere and is reflected back with a rapid reflection, because it's sporadic E that I'm modeling here. The reason this is curved, by the way, I'm not suggesting that radio waves go necessarily in curves like this, is that the ground on this picture is shown as horizontal. Obviously, it's not. So as the wave shoots up into towards the ionosphere, it's linear, we hope. As it enters the ionosphere, inside this magnetized plasma, a linearly polarized wave cannot propagate. It cannot exist. And it's because the electrons are constrained to move around the magnetic field, simplistically. And in fact, what happens, and this was established 100 years ago by Edward Appleton, is that it splits into two complementary elliptically polarized waves, the ordinary ray and the extraordinary ray. In the general sense, they're elliptical, and they rotate in opposite directions. And that's actually, by the way, the cause of Faraday rotation, which if you're an EMEer, you'd be familiar with. But in that case, they're both essentially traveling on the same path. But because the ordinary ray and the extraordinary ray travel at slightly different speeds, the refractive index is slightly different for the two. That means that by the time it pops out, if you're doing EME, at the other end of the ionosphere, the top, there's a phase difference between the two characteristic waves. They're called the ordinary and the extraordinary. And that means that the linearly polarized wave that emerges at the top is actually rotated, hence Faraday rotation. What happens when you're reflecting, losing the term loosely, away from the ionosphere, is that it's getting bent very rapidly back down to ground, and something more complicated happens. So there's possibly, that's what I'm trying to find out, a polarization change here. And so what comes down is a combination of the O and the X modes. In the northern hemisphere, the extraordinary ray downwards, because all these things depend on the orientation relative to the magnetic field, is right hand. As it comes out, they call it limiting polarization. You might read about that in propagation books. And that's just the particular combination of X and O that you ended up with when you came out of the ionosphere. And then that's received down the bottom, and that's what we're doing. And the polarization of the downward wave depends on the relationship, as it says there, between the X and the O. Right, so that's all preamble. So here's the experimental work, and this was the subject of my first paper published in one of the IEEE journals. So there's my antenna up there. So two identical antennas mounted on a common boom. They are, needless to say, a couple of centimetres misaligned from each other, so you had to compensate for that in the measurements. Identical length of feeder, feeding into a slightly upgraded Anan 8000 receiver, and then stored as I and Q data, digitally stored for each of those two receivers, which are coherent receivers. They're in phase with each other. And then there's the ability to put a calibration signal in to take out the amplitude and phase error that there might be between those two receivers. So the process, as it says on the right there, is actually store all the data and analyze it later. But then you measure the difference in amplitude and phase between the vertical and the horizontal. And you can do that. Most of my measurements have been done at 6,000 samples a second, partly because the software didn't go any slower than 6,000, not because I really expected to see variations that quick. And the answer is I don't, by the way. But then once you know the phase difference between the V and the H, you can calculate virtually everything else about the wave. So just to illustrate the sort of raw results that come out, this is a real plot. The three plots, the top one is the signal strength of those two, horizontal and vertical. Horizontal is the blue and green, vertical is the red and yellow. The yellow and green are smoothed. And you can see that there's quite a lot of the variation in the signal strength is common to both of them. So it's some other mechanism, it's not a polarization related thing. But, well, sometimes, this one's a nice flat one for illustrative purposes, but sometimes the polarization variation is quite considerable. So this middle line is I've called it the ratio of horizontal to vertical. In other words, the number of dB. And in the middle there, horizontal is about 6 or 7 dB stronger than the vertical. And also, this was like the first sort of, blimey, this actually does mean something, result. And I genuinely didn't know, and nobody could tell me, what phase difference I would see. And in fact, in this particular case, you may not be able to read those numbers, but that's a 45-degree line. And that is well outside well within the accuracy of the measurement to say that the phase difference between them is not 0 and it's not 180 degrees. Therefore, that wave is not linearly polarized. That was like the first sort of, okay. Because I didn't know whether that was what the result was going to be or not. So then, here's an example. So and I have reported some of this here before. Move on somewhat. I did a measurement campaign in 2018, gathering as sporadic E. It's sporadic, isn't it? So it's unpredictable. If you just sat your receiver on one particular frequency looking for one particular signal, you'd probably catch it once or twice in the year if you're lucky. So you have to take a sort of an opportunistic approach. But I gathered as much data as I could from as wide a range of beacons as I could. Because the thing about beacons, obviously, is they're on all the time. And they are more or less continuous, particularly the FSK ones. So here's an example. And what you can do by doing that post-processing is you can plot the shape of the ellipse. And this is sort of analogous to what Graham G3TCT stuff was doing, except this is more precisely calibrated. And also, it's showing you how the wave changes from something sort of close-ish to circular to being almost linear, but never really staying there, if you see what I mean. And on this plot, the blue represents it was right hand, so it's coming out of the board and it's doing that. And red is left hand. And this is a real recording, real time, by the way, as well. So that's how it was varying. It's over a time scale of large fractions of a second and longer. And this is normalized, so I've taken out the amplitude variation, the total amplitude variation. So the shape of this ellipse and position of this ellipse can be characterized by looking at, very simple, the ratio of the long axis to the short one, called the axial ratio, and the tilt. And that allows you to be precise about what the polarization state was at that instance in time. Now you can see on this particular one, it was varying all the time. But what I needed to do was be able to demonstrate that this is not just a one-off. It happened to be on that 3 o'clock on that afternoon sort of thing. So I've gathered a lot of data. As it happens, this is all actually on one day, this particular one, the beacon on the Faroes. And on the left-hand chart here, I've plotted that axial ratio, so the shape of the ellipse. The red line in the middle is the axial ratio equals 1, so it's circular. The linear, as I said before, I mean, you can imagine as this gets smaller and smaller and smaller and smaller and smaller, the axial ratio gets bigger and bigger and bigger and bigger. So pure linear is actually infinity. But you can see that I've plotted on a sort of a log scale here. So there's an axial ratio of 10, 100, and 1,000. And that's all the samples for about 40 minutes worth of data spread over a longer opening at 6,000 samples a second. So there are something like 20 million data points in that. So you can see on the left there that the polarization, it sort of wavered its way through circular, but spent most of its time at sort of 3 left hand or 3 right hand, bearing in mind that left hand is on the left of that chart, left of the red line, right hand is on the right. So there gives you an overall distribution of what the behavior of the polarization is. On the right hand side, you've got the tilt, this angle here, the angle to the horizontal. So vertical would be 90 degrees, horizontal would be 0. And this one, although it wavers all over, well, you can see from this, it wavers all over the place, but it has a clear preference for minus 60 degrees, which actually corresponds to the top left-hand, bottom right-hand quadrant. So the reason I've laboured that slightly is that on the next chart, I've got a lot more of these, and I want you to be able to see. So this is, I mean, obviously, to some extent, this is work that I had to do in order to satisfy the academics. But it does prove that it's a real effect. And by the way, the proportion of the time that it's linear, depending on where you draw the boundary, certainly if your definition of linear is a axial ratio of more than 100, say, well, it's hardly ever. It's certainly, the majority of the time, it's elliptical, even though this is actually a horizontally polarized antenna that's transmitting from the Faroes. So these are the results from the whole measurement campaign. So there's the one we were just looking at from the Faroes, and that's a path from, so the triangle in the middle is my QTH. Obviously, that's a great circle map. The red blobs are the beacons that I actually managed to capture decent quality data on. And you can see that the Faroes, it's wavering all over the place. Sardinia had a preference for right hand. Spain had a preference for right hand, but not very distinct. The Italian one also wavered around all over the place. And then these two are of particular interest, Slovenia and Hungary. Well, the first thing I should say about all of these is that none of them spent a significant proportion of the time as linear polarization. So what was transmitted as linear is coming down as elliptical, and that answers my question, in a sense, the research question. Is it magnetoionic or not? But really, you need to be able to explain it a bit better. And I can't do that yet. Because the thing that differs between, say, the path up to Faroes or down to Spain and the one that goes across here to Slovenia and Hungary is that the north-south path is parallel to the Earth's magnetic field. The east-west path is at right angles. And you might expect different things to happen. And you can see, even from these charts, that these two are much narrower distributions, and both in terms of the tilt, but also the actual ratio, the shape of that ellipse. But more to the point, they're different from each other. And that was a surprise, and I don't have an explanation for that yet. But it's an intriguing question. So level 1 question, is it magnetoionic? Yep. Can you actually explain the way it actually behaves in more detail? No, not yet anyway. So they're left and right. Now, I got a little sojourn into a bit of side research that I did. And that is because I needed to actually show that what I'm measuring here is actually sporadic E rather than something else. Yeah. So I went into, can I get some measurements that shows that there was sporadic E present on those days? Now, the professionals have a range of techniques for studying sporadic E. ionosondes there is like the gold standard, if you like, for identifying sporadic E, and I can show you that how that works shortly. You have got satellites up there which are specifically designed to monitor the signals from navigational satellites as they're occulted, eclipsed by the Earth's atmosphere. So you can measure it using those GNSS things. There's incoherent scatter radar, if you've ever heard of the RSGB, radio telescope and radar systems, sadly fell down. And then you've got these rocket studies. And basically, the rocket studies are great, but you know they only apply when you shoot a rocket up. The ionosondes are on all the time, but they're not everywhere. And that's a map on the right there of all the ionosondes in Western Europe that operate 24 hours a day. There are some huge gaps there. When you think that your sporadic E cloud might only be tens or 100 kilometers wide, there's an awful lot of gaps between them. So I turned, having been stymied on this particular issue, to using amateur radio data. And this is the subject of my second paper. Not the first person to use amateur radio data to study the ionosphere, but the first one to apply it to sporadic E. So on the left, you've got a chart rather similar to what you'd get if you went onto dxmaps.com, which is actually where I downloaded all this data from, by the way, because it aggregates from multiple sources. You've got all the tracks joining them. The blue ones are 6 meters. The green ones are 10 meters, and there's a red one. You need your eyes well adjusted to see the red one, which is actually about there, which is a 4 meter, a single on this particular time period 4 meter spot, and that's like 15 minutes worth of data. But I've also added the midpoint of that path, of the Great Circle path, because that's where the sporadic, well, roughly where the sporadic E patch is likely to be. And in the right hand, I've actually taken the lines actually obscure what's going on. So I've taken that off so that the big blobs show you where there must have been sporadic E at that time. This won't be news if you're used to watching the charts on dxmaps.com. The very fine stuff in the background is an indication of the coverage of the measurement, because the thing about amateur radio signals is you don't know who was on. They may or may not have been listening, they may not have been transmitting. So the only way to know is to look at the people who were actually reporting somebody's signal. So the people who were received or the people doing the reporting. And the little dots are all the possible paths that the stations that I know were on the air in that 15-minute period actually were at. Okay, I'm not going to spend time on ionosondes other than to say, you see that straight line at the bottom on this ionosonde is a vertical echo sounder. It uses the time delay between when you transmitted it to when you received the reflection back to tell you effectively the height of, and various other things. Sporadic E comes out as a straight line because it's thin. F2 propagation like this comes out curved because it's being bent much more slowly, and also the wave slows down as it passes through the ionosphere. So there's this upward curve, and it slows down more the higher the frequency, until you get to the critical frequency, the maximum frequency that can be reflected by that particular level of ionization. And this is from the ionosonde in Czech Republic, or Czechia, or whatever they call it. This is another one, just to illustrate that actually sometimes the sporadic E gets so strong that it virtually obliterates the F layer stuff above it because it's too thick. You can't see the F layer through it. And the frequency that I look at is actually this. It's called the top frequency. So it's the highest frequency reflected at that location. It only really tells you what's happening in a sort of a cone immediately above the ionosonde, but it's all we've got. So I then can plot it on a map, and I'll show you a quick video. So there's the map. There's that estimated coverage that I talked about. There's the PSKR reports, the DX cluster reports, the reverse beacon network reports. And by the way, you can see that there's a big patch of sporadic E on this particular one over here. and there's a big patch over there, and there seems to be a gap in between. Now, is that a real gap? Well, actually, we've got lots of these little coverage markers in that gap, so it probably is real. The final thing to add to it is the ionoson figures, because this is what demonstrates to the scientific community that this is actually valid, that it actually is a good indicator of the presence or otherwise of sporadic E. Nothing is perfect. Clearly, there are all sorts of assumptions based around this. But so you can display the progress, and these are successive 15-minute samples, and you can see that it's what you would have observed is that it started off with a big blob over this sort of region. It then split into two blobs, one over there close to that ionoson actually, and one over here, and then it generally moved that way and got thinner. And you can see on this one, this is the last one. Most of the blobs are green, and there aren't blue ones or red ones. So in other words, you were getting sporadic E at 10 meters, but not at 6 meters. And these three ionosons over here have essentially stopped observing any. There's no straight line on the ionoson plot. So there was method in my madness in choosing that particular day, because I've actually want to look more closely at two particular reports of two sets of measurements that I did on Slovenia and Hungary beacons. There's the path from the UK, or rather from those two beacons. You can see the midpoints, which is those the red diamonds, were very close, well, within 100, 200 kilometers of each other. And there's the live signal from the Slovenia beacon. And there's the live signal from the Hungary beacon. They're rather different. And yet the path length is not far different. The angle of the magnetic field is not much different. And the two reflecting points are very close together, relatively close together. So some sort of instrumental error. Oh, by the way, sorry, the other thing I should say, if you look at the time clock at the top there, this one is 10 minutes after that one. So it's the same afternoon. 10 minutes time difference between those two. So that pretty much rules out any kind of instrumental effect that could be going on here, or even a gross change in the distribution of sporadic E. And just to go to those charts again, these are just those two, the Slovenia and Hungary. So across 4 days, 4 different days, once I saw that there was this anomaly that I couldn't explain, I focused on these two from the point of view of gathering data. So across 4 different days, that distribution, the shape of that ellipse was retained. Ditto, in fact, across 6 different days. And the Hungarian beacon, again. But, I mean, there's more spread on the angle, and that's related to the thickness of the sporadic E layer, I think. But nonetheless, there's a very, very consistent pattern between those two, and I need to be able to explain that, or at least somebody does. And this is the third paper, which I'm working on now. And the idea is that my PhD is going to be paper 1, paper 2, paper 3, and a bit of explanation around it. And Bob's your uncle next April. Well, we'll see. So this is where I am. So there's my 2 questions. That's interesting. And it was interesting, and all the recordings showed elliptical polarization. None of them showed a significant proportion of linear polarization. Actually, the time it spent truly circular was quite limited as well, as it happens. But I think that's because it's changing rapidly. So therefore, strong evidence. And so I'm talking about the mechanism. I'm not talking about how sporadic E is formed, by the way. Jim talks about that. He'll talk about that tomorrow. So it's magnetoionic, and you have to take account of that when you're looking at the effect of sporadic E on radio signals, whether they're being reflected back to the ground or whether they're passing straight through. And there's a bunch of factors which I don't yet understand. I've done a certain amount of modelling, ray tracing, but don't have an answer. And it probably depends on the geo field. and other things. So the other question, can I use this to work more DX? Well, I was sort of hoping that the best polarization for DX would emerge from this, that it would be right-hand circular or left or whatever, but they show the full range there. You can definitely see the full range. So it's not a magic bullet, but it is a fact that the MUF, the maximum usable frequency for the extraordinary ray, is slightly higher because it gets bent more sharply than the maximum usable frequency for the ordinary ray. So if you can align with that, it might give you a small advantage. And the money where my mouth is, this is I am almost finished, Dave. So my station here, you've got a stack match which is designed for stacking 2 antennas, but I've got it feeding the 2 left vertical and horizontal. There's a quarter wave phasing line there, which then basically, because that's the horizontal antenna, makes it produce right-hand circular. And then I can switch in an extra half wave, which, because 270 degrees of angle as you go along that sine wave is the same as minus 90. So it gives you a left-hand circular, and that is the end of my talk. Oh yes, sorry, just to say, just the last couple of weeks I've been receiving some signals on 6 which I think at least one bounce was actually F2, and they were definitely stronger on right hand than they were on left. It's not quite as simple as that, though, which I can go into if anybody's interested. The other thing is, which is absolutely stone bonk fact, is that in my area, I live on the edge of a village, so it's not that noisy, but I have one particular direction towards the village, which is noisy, and if I switch to right-hand circular, it reduces that noise level by about 6 dB. Versus horizontal. So I'm keeping this, if only for that reason. Anyway, so that's that. End of talk.
Thank you very much, sir.
Mr. Conte.
So we got hundreds and thousands, but we got no silver bullet, have we?
No silver bullets. Hundreds and thousands.
Time for a couple of questions. Yeah, first one.
Going to give him a microphone.
Thank you. Hi, Chris. Lee, G0MTN. Fascinating. So just where there's so much variation between linear and circular and left and right, if you've collected all of the samples in the processing, is it then so possible to extract the signal from the noise by finding exactly where it is and then extrapolating that? Might that one day be possible to do in near real time, so you could collect the data and find signals that you weren't going to get just by picking an individual azimuth?
Even though a linear antenna will only be 3 dB down on a circular wave, but nonetheless that could be the 3 dB that gets you the QSO, or you lose. In principle, yes. And of course, MAP 65 on the EME world does a sort of an approximation of the combination of the horizontal and vertical to produce the best decodes. That would be the vision, yes. But as you say, doing it in real time is quite tough.
Yeah, super, thank you.
Yeah. There's one down here, Dave.
Yeah. Quick one. In the first one you showed horizontal,
the very first one.
Yeah, the red and the black.
Yeah.
The noise floor on the red is about 6 dBs higher than the black. Why?
Well observed. Well, that's because the red is the vertical antenna, and the noise in that particular direction is stronger on vertical than horizontal. I mean, there may have been, actually at that point, I hadn't fully calibrated the losses in the cables and all that kind of stuff, whereas the later data has all of those things calibrated out.
Any more? Yeah, Jim.
Oh, this is going to be a tricky one.
I was just going to say congratulations on a really fascinating talk.
Thank you.
And my follow-up question is, having
This is where the knife goes in.
yeah, no. It's just intriguing that if your diagrams confirm that what comes back is very rarely for any length of time linear.
Yeah.
Have there been any attempts to do experiments between here and say beacons on different circular polarization to do circular from each end, if you like, to see what that might produce?
Good
in
question.
terms of
Of course, there are, at least at 6 meters, very few. Well, I don't think there are any circularly polarized beacons, because making omnidirectional circularly polarized antennas is actually quite hard.
Yeah.
I think they manage it for mobile phones and stuff like that, but they're very complex things. So good idea, but no, we haven't. Nobody's done that yet.
And as an adjunct to that, is there any information coming out of your work about how rapidly the polarization changes? Showing the rotation of the ellipses
of the axis, yeah.
So does that what does that relate to? Does that relate to the season, the time of day, the area?
Wonderful questions, Jim. I've done some modelling which shows that the extraordinary and ordinary ray, even though they are nominally elliptical, at this high frequency, 50 megahertz, they are very close to circular. Right? If you can assume they're circular, then the angle, the tilt angle, depends only on the phase difference between X and O. So the rotation, like the Faraday rotation, is when the phase difference is changing, which is presumably because the reflection's coming off a different part of the blob as the sporadic key blob moves past, and the phase difference depends on the rate of change of the refractive index within the layer. Yeah. So the interesting thing about this from a scientific point of view is that in principle you could find things out about the structure within a sporadic key layer. Be quite difficult to deconvolute everything, but you know. Yeah. But the thing that's more difficult is understanding what drives the axial ratio and the rotation sense, because that is related to whichever of the two, assuming they're circular characteristic waves, is stronger, and what's causing them to vary differently from each other. You saw that the overall fading pattern was actually quite common between the two. So what is it that makes them do different things? And again, it could be the shape, could be physical morphology of the cloud.
And would it be different on different bands? Would you have different rates of rotation?
Probably, yeah, because if you like, the number of wavelengths that you've got within the reflecting layer is different. Although obviously on 10 meters, the ionization doesn't have to be as thick to reflect it. So,
fantastic.
I can answer some things, but not everything.
Very quick one.
Very quick, of course, the meteor beacon is circularly polarized.
Of course it is.
It beams up, right-hand circular polarization.
But out horizontally,
who knows?
Yeah.
Right. I'm sorry. I'm going to have to. Well, I'm going to have to draw it to a close here. But thanks for a fascinating talk. Yeah.
Thank you.
That shows appreciation.